Welcome to this webinar. I think we could start. This webinar is being recorded, so we will have this webinar also uploaded to our website. So if you want to see it later, there will be no problem. You will receive an email from us with the link once it is uploaded. In the meantime, at the bottom of the screen, you will see in Zoom, you can ask some questions through the chat. If you have any questions during the webinar or maybe at the end, and our speakers will be happy to answer. So welcome. Thank you very much for joining to our webinar of functional materials. We're going to learn why testing methods are critical when evaluating your options. And here we have Chantal Van Sambik and Andrew Graves, and maybe Andrew Gardiner will join later. Chantal from Nexeo Plastics. Chantal is manager at Nexeo Plastics of the inside sales team and additive manufacturing in EMEA. And she has over 25 years of experience in plastics and additive manufacturing, with broad experience in several fields, which include sales, application development, business development. And well, Chantal, I pass you the floor for your presentation. Thank you very much.
Thank you, Victoria. Yes. Okay, some words about Nexeo. We are a global company with a revenue of more than $2 billion, more than 700 employees, and we have more than 50 world-class global suppliers. Some more numbers. So we have 11,000 customers in different market segments, like automotive, interior, exterior, under the bonnet, healthcare, packaging, which means rigid packaging, or also flexible packaging like film, E&E materials, E&E market, so electronic market, wire and cable, and of course we also are active in 3D printing, where we have also customers. We have 9,500 products, and we are distributing these ones in more than 60 countries. Okay, so what is Nexeo Plastics? We are a company which is already existing for 50 years. So we are celebrating this year our 50 years existence. And all our life, we were working in the plastics industry. So we are known for all the different technologies for plastics processing, like injection molding, like film, like blow molding. And then in 2015, we started to work in the 3D printing business unit, which is a different technology of processing plastics. So with our knowledge in this plastics, I think we have a very nice tool in our hands to be successful in the 3D printing. What do we do in 3D printing? It's the filaments, it's also powders, it's pellets for FGF printing. And today we will talk about resins. So you see here all the suppliers we are working with. You see still the Covestro logo, which now, of course, is Stratasys. If you can pass to the next one. Yes, and then a few words about why we are a little bit different. I think we are known for our application development team. We are doing material selection for the opportunity or for the project which our customers have. That means that we are looking at the part. We think about what are the requirements of that part and decided which material, because we have materials from polypropylene, ABS, until up to PEEK, PPSU. So we will look based on the requirements of the part, which material is the best solution for the part. And this is not only for prototyping, but also for real production of the parts. So this is where Andrew today is going to give you some more things or testing methods, what we use, how to select the right material for the right products. So Andrew, may I ask you to to lead the rest of the presentation. Thank you.
Thank you, Chantal. Hopefully you can hear me.
Yes.
And oh, my I don't know what's going on. What's going on? Sorry, I've just lost the screen view. I can't see the slides. Can anybody else see the slides?
No, but Victoria, can you?
There we go. They're back. We'll put those in. Can I advance them if we put them in?
Yep.
Okay. Okay, so my colleague Andrew Gardner has just joined. Now, hopefully I can advance them. Do I have the permission? It doesn't look like it. That's maybe okay. That's not me doing that. I don't have the ability to move these. I need the ability to move these slides. Victoria, I think you need to give me
I can do it for
permission.
you, Andrew. If you just tell me to.
Yeah. Okay. Well, that's not really going to work, but okay. We're going to have to do that, I guess. Yeah. If you could work out how to give me permission, as we talked about before, that'd be great. Okay. So first of all, a little bit of an update for those of you that don't know. We started life as DSM. Some people know the Somos materials, the photopolymers. That business was acquired by Covestro, so we were Covestro for 2 years, and that business is now being acquired by Stratasys. So we are now part of the Stratasys team, working on the photopolymers and also powders. So what we're talking about today is some of the work that we've been doing on photopolymers, and remember that picture on the left, because I will come back to it in a second. Next slide, please. So I want to talk about a little bit about cars for a start. Here's a couple of my cars. One which I still own, the lovely 1968 MGB, and the car that I just sold, which was a Seat Leon Cupra. Over 50 years between these cars, a lot has changed in 50 years, not least of which is power. The MG came out of the factory with just under 100 horsepower. I've bought it out and just under 2 liters. It now has, with upgrades, about 130 horsepower. The Seat came out of the factory with just under 2 liters and 300 horsepower. So a lot of difference there. Yes, as I promised on the LinkedIn profile, there's a cute picture of my Springer Spaniel. So yeah, next slide, please. So big changes in power, but also in materials. As you can see, there's the grille and the bumper of the MG, beautiful chrome, lots of metal. Next slide, next click. And there's the same picture of the Seat, where everything is now plastic. Big changes in 50 years. And no, those are not my number plates. I'm just very good with Photoshop. Next slide, please. So what else has changed? Well, door mirrors. There's the nice metal, shiny chrome door mirror of the MG and the plastic version, which we're all familiar with on modern cars. Next. And of course, also door handles, lovely chrome metal door handle, which is replaced by plastic these days. So if you're an automotive manufacturer and you used to use metal for these things, how can you ensure that using plastic, these parts are not going to come off in your hand or break or just crumble into nothing? Well, of course, the answer is testing. Next slide. And there are various ways of testing, and of course the ultimate, which plastics companies and paint companies do, is put samples out in the Arizona sun or the Florida atmosphere with lots of humidity, and they do that for years. Well, that of course is real world testing, but if you can do the next click, the way that you get fast results is by accelerated testing, and there's a number of ways of doing that. You can test for just UV, and that shows a picture of a QUV tester. Now, we used to use a QUV tester in our facility in Chicago, where our resins are developed, but it now sits under the stairs, and we don't use it anymore because it literally only tests for UV aging. We now use what is called a Q-Sun tester. There's a picture of it there, which is a full environmental simulation of the real world, and I'm going to explain that in a little bit. All our materials that we are developing, and even some that already exist, are now being tested in a Q-Sun machine. Next click. So the thing is, if we want to move into end-use functional applications with additive manufacturing materials, we need to be testing them to the same rigorous standards that the plastics industry uses. And that's really what we're going to talk about today. So next slide, please. So do you remember back cars in the 1980s when the plastics using those really weren't that weatherable? There's a picture there of a 1980s car, and the plastic is deformed and cracked and discolored. And as an example, Delrin is a material that is used in automotive, and there's three charts there. The one pointing straight, almost straight down, the 00 version is a very early example, and as you can see, its glossiness dropped drastically after just a short exposure, and the next version of that was slightly better and it lasted a bit longer. And then the current version of Delrin that is used, no matter how much exposure, it doesn't lose its glossiness, and that's what we see in modern cars today. So these kind of accelerated testing methods are used in the automotive industry and other plastics industries, and that's what we need to be doing in the additive manufacturing world. Next slide, please. So when we talk about functional materials, what does that mean? And if you can click through the next one. Functionality is linked to an application. So different applications require different functionality. But it is related to long-term stability. We need these parts to have not lose their properties over a long term, whatever that means for that application. Next. And there are, of course, standards, as we've talked about. There are standards for testing these. Now, because our materials are photopolymer materials developed in the USA, we are very familiar with the Society of Automotive Engineers and their testing. And one of those is J2527 for exterior applications. And that is what uses a xenon arc weatherometer for testing. And that is that Q-Sun machine that I talked about. So that's why we use that machine. That's why we use these testing, because it is a recognized standard in the automotive world. And of course, there are similar standards in Europe that will be very that will relate to this as well. So next. Another thing that we hear quite a lot is, well, DLP printers are for printing end-use parts, but not stereolithography, SLA. And we say, well, why do you say that? The printer technology and the light engines don't provide functionality. That comes from the chemistry and the way you cure it. So stereolithography parts can be equally as functional as DLP parts, and that's something that we're very interested in the Stratasys world, and we hope to bring you more stories about that coming up. So next, please. So the entry tickets to functionality, the properties that we're talking about, the properties that need to be stable. What are they? Well, of course, dimensional stability. You don't want the part to warp or change shape. The part has to remain tough over however long it is required for that application. You don't want it to creep. You don't want it to stretch. It has to have fatigue resistance, and it has to have environmental stability for whatever that application requires, whether that's outdoors, indoors, high heat, whatever. Next, please. So there's a lot of talk now about end use and functional parts, and people will show this on their data sheets. But we've taken some of these, what I'm calling first generation functional materials, And we've actually put them through our Xenon Arc weatherometer, our QSun machine, to see what happens. And as you can see by the red boxes there and the red arrows, some of these properties, modulus, elongation, stress, can change drastically. Next, please. So you can see on the bottom line, the blue line, which is 90% relative humidity, there were significant property changes with these materials after only 32 days. 52% drop in modulus, 50% increase in elongation. Next. But as the yellow line shows, even with low humidity and high heat, there were changes as well. So both these things are important, heat and humidity, as well as UV, of course. Next. And you'll see that they were for a very short period of time, only 32 days. So as an example, I had a part that sat on my desk. If you just one more click, you will see that this part was a next click, please. This is a part that sat on my desk, and I used to demonstrate it on Teams calls during the pandemic to my team, and I squeeze it, and it was very flexible and very tough. And after about 3 months, I did exactly the same as I'd been doing for months on these calls, and I squeezed it, and it shattered into 27 pieces all over my desk. So this was a part that, when I received it, was tough and relatively flexible, and after only 3 months of sitting in an office environment, shattered into many pieces. So a physical example of what that chart is showing, that these properties can change even though a material is declared as functional. So next, please. Of course, weather resistance is a key part of this, and weathering factors are solar radiation, heat, and water. Next. And all of those will change the chemical and the physical properties of the network of these polymers, leading to deformation, loss of gloss and color changes, as we saw with those 1980s plastics in the car, and of course, degradation of mechanical properties. So these are the things that we need to be aware of and need to look out for in our additive materials going forward. Next. So proper test is critical. So here's a bit of a chart, but you can see along the bottom, that's the wavelength of basically sunlight going from the ultraviolet on the left up to infrared on the right. And the irradiance is shown on the vertical scale. And that middle line indicated by the blue arrow is the spectrum of noon summer sunlight. So obviously it includes everything from UV to infrared and visible in the middle. And the line at the bottom on the left is that QUV tester that I was talking about that only tests for UV. And as you can see, it's a very small part of sunlight spectrum. So the QSun tester that I was talking about that we now use is that top line, which is a Xenon Arc lamp, and it very closely replicates sunlight. So that's why we use that tester. That's why the automotive industry and the plastics industry use that tester. QUV only replicates a small fraction of the sun spectrum. So that's why we use the QSun tester, and as it shows there, the SAE J2527 automotive test is the one that we use, and that replicates sunlight very closely. Next. Here, oh, can you just go back, please? We see on data sheets very often, this material is tested to ASTM standards. And then if you look at the small print, it will show you which ASTM standard. And for example, if it just says G154, that is only QUV testing. So you've got to be careful when reading data sheets and really look into that, what kind of test was actually being used. Next, please. So, as I said, we use J2527. It's an accepted standard for exterior weathering testing. Next. And this is the test cycle. It goes over and over again through all this cycle. Obviously, there's high UV on that throughout the whole test. but the parts are put through high relative humidity in the dark, and then the temperature is ramped up and in the light and medium humidity, and then the parts are sprayed with water as well, so you get humidity and you get water spray, and this cycle goes over and over, day in, day out, and every so often, of course, parts are taken out and tested so that we can see the effect after various periods of time. Next. And of course, all the properties will change, but elongation at break is a very good indicator of your property changes. So here's a chart of one of these first generation weatherable DLP materials. And the bottom blue line you can see is the elongation at break straight out of the printer, T equals 0. And it goes up to 23, something like that, which is great. But then, as the chart on the right shows, as time goes on, goes through this testing in this QSUN tester, the elongation goes down right to the point that after 600, 700, 900 hours, you're only getting something like 3% elongation. So, as I said, all the properties will change, but elongation is a really good indicator of how this is happening over time. Next, please. So this is a chart showing one of these early DLP materials and what happens to elongation at break if you put it through that old QUV tester and you put it through the QSUN tester using the J2527 test. And just using the UV tester, you can see that it's not too bad. It only loses 20% of its elongation after 450 hours, and after 1,000 hours, it's only lost 60% of its elongation. But if you put it through the full weatherable testing with all the heat and light and humidity and spray and UV, after 300 hours, it loses 80% of its elongation, and it just drops from there. So you can see why we are very keen that materials should be fully tested with this weatherometer. Next, please. So as I mentioned earlier, we actually went back and we're starting to test some of our older materials that have been around a while. And for example, one of them is watershed black. Now, this is a stereolithography resin, runs on the Nexeo machines. This was never designed to be a weatherable material. It was designed as a prototyping material. But we thought, well, we'll put it through this Xenonarc weatherometer QSUN tester. And you can see there's that same data from before, the competitor's resin with the UV, just the UV testing, and the bottom line is with the Xenonarc weatherometer testing. And there's the black line showing what the watershed black stereolithography resin did using the full weatherometer tester. And you can see that actually it performed better than this DLP material, which is sold as being weatherable and functional. This was a kind of a surprise to us because, as I said, this material was only developed as a prototyping material, but we're seeing that it actually performs quite well and even better than a DLP weatherable material. So this was kind of good news to us. And if you click the next, I'll show you a couple of pictures of the parts, the dog bones that came out of the weatherometer after this testing, and there's the watershed black parts at the top. Even after 1,000 hours of aging, they were still flat. The DLP materials, after 1,000 hours, were bent and distorted. And going back to one of those previous slides, one of the things that you need your part to be when you're developing it for functional use is for dimensional stability. So quite important. And again, a real surprise to us how well a stereolithography resin performed under these really strenuous tests. Next. So as I said, yeah, it performed better than one of these first generation weatherable DLP materials. Next. And a real world example of that is a part, it's an electronics enclosure, it has two halves, they have to fit together. It's not a real part, it's just a part that we created to demonstrate this. It has two halves, very similar looking, and if you click next, you will see that in these first two first generation materials from a couple of competitors. They do not meet up very well after going through weathering. There's a large gap in the middle of the first one, and the bottom one it meets at the bottom, but not at the top and not at the back. And then the third picture is a developmental material. Still says Covestra on there, but it's now Stratasys. And this is a DLP material. So this is something that we are developing for the P3 platform, for example. A DLP material, and you can see that that actually performed really well. After 1,000 hours of testing, those two parts still fit together pretty well. Very slight gap at the back there, but a lot better than the other two materials. Next. And so here's that data for that material added to a chart showing, if you just click the first click, competitor one, the red line, that's the one that we saw previously. Next click. The blue line is another competitive material, performs slightly better, but again, after 1,000 hours, it still lost 80% of its elongation. Next click is this developmental material from our lab in Chicago, performing considerably better than the first one, and even better than the second competitor's material. And going right up to about 1,350 hours before dropping down to 80%. So are we there? Are we where we want to be? Not fully, but we're better than some of these other ones that are available, and we're still working on developing these materials further to give you the best materials for your application. Next. So some conclusions. I think if you just click through these. Property stability, we need to be measuring this using industry standards, the standards that the plastics industry uses, that the automotive industry uses, because they recognize these standards and they understand these standards. Next, functionality is linked to an application. So automotive applications are very stringent, the other applications not so much. So parts should be tested relative to what the application requires in terms of its environment. Some are more strict than others. Next. As I mentioned, technology, for example, DLP, that does not determine functionality or the durability. It is the chemistry. And sometimes, as we showed with watershed black, existing materials might already meet your needs. So, talk to us about that. Talk to Nexeo about that. And if you're looking for end-use parts, you're looking to produce end-use parts, make sure you ask the right questions about the material testing methods. When you see on a data sheet that a material was tested to a particular standard, do a bit of research, see what that standard was. Was it just UV? Was it full weatherability testing? These are the sort of questions that you should be asking. And I would like to just add that a recent panel at AMUG last month, there was a lot of discussion about all material suppliers should be using the same standards on their data sheets when we start talking about end-use materials, because if we don't, we just end up confusing you, the end user. And if we all use the same standard, then you can look at all the materials available and choose whichever is best for your application. So hopefully at some point in the near future, we will all be showing the same data on our data sheets. I think that's it. That should be the end. Yes, that is it. So I am done. Thank you very much for your attention.
Thank you very much. Thank you, Andrew. Now is a moment of questions. You will see all the participants in the webinar. You will see that you have here an icon with a chat. So if you have any questions, write them through the chat and our speakers will be happy to answer. Let's see if there come any questions.
Don't be shy. Don't be shy. Ask us anything. We may not be able to answer it, but you can ask us anything.
Yes. I think everything was so clear that they do not have any questions.
Well, we do try. We do try.
No, I think it was very interesting, very focused, and of course very clear because we don't have questions.
Very
Well,
good.
that's good.
Yeah, if there are any questions later on, just yeah, connect with us.
Yes, exactly. If you have some questions later on or you want to reach to any of the speakers, do not hesitate to contact us at this email, welcome@nexeoplastics.com. And of course, we will be happy to answer you. And in the following days, we will upload the webinar recording to our website. Those of you who register or assisted, you will receive an email with the information, and you will be able to see it again, and maybe then there come some questions or requests. And yeah, oh, well, here comes one question from Pierre Solo Malala. And do you test other liquid than water?
Yes, we do. So this is what we're particularly talking about here is weatherability testing. But there are, of course, other chemicals that need to be tested, petrol, gasoline, oil, and so forth. And those are also important, again, depending on your application. So if you have a part that's sitting in your office, you obviously don't need to test with oil and gasoline. So for particular applications, certain materials that are targeted at that coolant, yes, example coolant, those will be tested based on their applications. And as I said, this is a new area for everybody when we're now talking about using photopolymers for end-use parts. You know, you go back 10 years, these materials were just for prototyping. Some prototyping does involve these liquids, coolant, for example. We have some historical data for some of our materials, but as we move forward, as we get into more materials specifically for end use, then yes, these tests with other chemicals will be carried out, and they are important.
Good, thank you. Thank you, Pierre, for asking. Any more questions before we go? Well, as I said, thank you. Thank you to all of you for attending. Thank you for joining, and we can keep in touch through this email. We'll be happy to hear from you. Thank you very much.
Thanks, everyone. Thanks for joining us.
Thank you. Bye.
Bye-bye.
Bye.